continuing from the last video where we took a look at the transition matrices of the various bias functions coming from the Wirewalk algorithm, I actually wanted to take a look at the random walks that arise from those transition matrices. So note that in the paper we're performing 10 walks of length 80. So on each walk you'll see 80 nodes. And here we have the Karate Club graph, which has 34 nodes. And I've actually gone ahead and for 10 walks of length 80 visualized all of the walks for the various bias functions. And as you can see, it's very hard to interpret. And so just so that we can understand what we're looking at here, I've looked at the first walk for the first node. So this is node 0 in the network where we're performing a walk of length 80. So we will see 80 other nodes. And then we would repeat this for this particular node a certain number of times, but here we're just looking at it one time, the first time. So we have the Tversky walk, the Levenstein walk, the resource allocation walk, the Sorensen walk, the Sultan walk, hub depressed walk, hub promoted walk, preferential attachment walk, LHN walk, common neighbors walk, Adamic adder walk, Jacquard coefficient walk, min cost max flow walk, and max flow walk. And something I'd like to touch on in this video is why I need mathematics for the Wirewalk algorithm. So in particular, we took a look at the transition matrices. I want to study properties about the transition matrices that I've introduced in the paper. I want to understand how the underlying graph is stretched because that transition matrix can be treated as an adjacency matrix. I want to see if making the graph more sparse, in other words, only allowing the random walker to travel to nodes that can be reached in k steps, may impact the runtime and performance metrics of the algorithm. And I want to see if there's any transferability of this material to the magnetic Laplacian. I would also like to continue my study of the magnetic Laplacian as it applies to directed networks. And as I just showed you, we took a look at the biased random walks. I would like to study how the resulting walks from the transition matrices differ across the bias functions. I may need multiple time series analysis or something different for this. Reviewer 2 left the feedback that, why not simply adjust the random walk-based embedding algorithm itself to have a certain bias, i.e. to include a biased random walk. And so what I think this feedback is getting at is, why not incorporate this bias into the neural network, the word-to-vec model itself, rather than having to change how you're actually performing the walk. And then they also mentioned it would be of interest to compare these ideas for other embeddings and data sets as well to see if this provides a generic improvement. And so that's something we touched on in the last video, which was, does the Wirewalk's performance hold across all graphs? And then, the last pillar I'd like to touch on is correctness. Lastly, I need to prove that my code is actually doing what I expect it will do. When asked to report about the correctness of my work, reviewer 1 and number 2 respectively stated, it was most probably correct and then also probably correct. I want to hold myself accountable for having a proof for my code. Namely, I should note that, I'm relying on a couple of packages, so this brings up the question, how do I write a proof for the, correctness of the word-to-vec model? Did, the GenSim library, provide a proof for that? Also, how can I trust the sklearn library? Are there proofs for their work? I believe it is all open source, so if there isn't already, I should be able to write those proofs. Thank you.